Hello students, in this video we are going to start with some linear algebra. So basically we learned about some linear algebra in the preliminaries itself, but now we are going to discuss a little more. Okay, so first of all we are going to start with something called the eigenvalues and eigenvectors. Okay, eigenvalues and eigenvectors. Right, so what is it? So let's say a vector v, yeah, is an eigenvector of a n cross n system. Okay, so basically given a n cross n system, the eigenvector will be given like so, matrix A. Okay, if V is a non-zero solution, to the system of linear equations What are the equations? A minus lambda I times V is equals to 0. See, if V is equals to 0, of course A minus lambda is equals to 0 for all lambda, right? But the thing is, basically we are looking for a non-trivial solution of this system. Clear? And this quantity lambda is called the eigenvector, right? It's called the eigenvalue, sorry. It's called the eigenvalue of A. Clear? Okay. So this eigenvalue and eigenvector, the definitions we already know, so it's not a very, I'm not going to discuss it further. Okay. Now the thing is, you see, we are going to start with this. So essentially, what is our goal? Why are we suddenly started with eigenvalues and eigenfunctions out of nowhere? Essentially, we want to calculate exponential of a matrix, right? And let's say for a big matrix, let's say 3 cross 3 or 4 cross 4 matrix, 5 cross 5 matrices. Okay, this is the best way that I know of to calculate a matrix exponential. There are other ways, there are many different ways of doing it, but this is the most intuitive and modern way of doing this. Okay, so first of all, let's look at this property, or maybe let me write it as a theorem. Okay, so before that, let us put down a small remark. Okay, now of course I am assuming that you guys already know what eigenvalues and eigenvectors are given a matrix, and what are the properties. So I am not discussing it further, but anyways, as a remark I am just writing that let lambda 1, lambda 2, lambda n, okay, are real and distinct eigenvalues of A. Okay, with associated eigenvectors, vectors given by v1, v2, vn. Okay, then what is the relation between these vi's? Then vi's are linearly independent. Okay, li. So I am not writing this thing, it is linearly independent. Okay, right. So with this we are coming to the important theorem. Okay, so theorem. So try to understand this theorem and you will understand what's happening. So essentially, let's say that if you have a matrix with a real distinct eigenvalues, okay, so let A n cross n matrix essentially has real and distinct eigenvalues eigenvalues. Okay, then what can you say? Basically it means that the matrix is diagonalizable. So basically then there exists a matrix T which is a n cross n matrix again such that okay, T inverse A of T, okay, that will be given by nothing but this very simple matrix given by lambda. So basically lambda n. So everything, all other off diagonal entries are basically 0, and this is the diagonal matrix with the entries lambda 1, lambda 2, lambda n. Okay. So very simple. Now why is it, let's say if you are in this situation, why is this important? Because we know that if we can do something like this, exponential of T inverse AT, if we have to calculate, let's say if we can calculate something like this, if you want to calculate something like this, it will be nothing but T inverse exponential A times T, right? So an exponential A, so you see, as a remark, if your matrix, let's say a matrix B is nothing but lambda 1, lambda n, 0, 0, okay, then it is easy to say that exponential B is nothing but e to the power lambda 1, e to the power lambda n, 0, 0. Okay, so you do realize that calculating the exponential is going to be very simple. Okay, if you can show that the if it is real and distinct, if you are starting with a matrix which is real and distinct, then what happens is it is diagonalizable. Okay, then you can write it in this form. Okay, and once you can write it in this form, essentially what happens is calculating the exponential gets very easy. That's the idea. Okay, so let's look at this theorem. So what does the theorem says? It says that if A has real and distinct eigenvalues, then you will have a matrix, clear, such that T inverse AT, when you calculate T inverse AT, that is going to be a diagonal matrix. Okay, we can also write this thing as diagonal lambda 1, lambda n. Clear? How do you prove something like this? Proof is actually easy. Proof. See, here what we are doing is basically we are taking a change of variable here. Okay, so let Vi be an eigenvector associated with lambda I. Okay, so Vi is an eigenvector associated with lambda I. This is what we are assuming right now. Okay, and what happens is, now see, we want to write down that I mean, we have to find that transformation T. See, the thing is, you are given a real distinct this matrix, right? Okay, with a you are given a matrix with a real distinct eigenvalues. Okay, now you have to find a transformation which actually reduces this to a diagonal matrix, right? So essentially what you are trying to do is find a change of variable which actually reduces the matrix to a diagonal matrix. Think of it like that. Okay, so what we are doing is this. Now you define T, clear, such that T of EI, okay, is nothing but Vi. Clear? So you see, since lambda 1, lambda 2, this is distinct, okay, lambda n, they are distinct, the corresponding eigen vectors which you are going to get, let's say V1, V2, Vn, they are linearly independent, right? Okay, so let's say if I map E1 the first basis element, that is to V1, E2 to V2, En to Vn. Okay, then what happens is I have a one-to-one map, right? So basically this is a this is a valid change of variable. That's what we're trying to do here. So when you define T of Ei to be Vi, okay, and what is Ei? Ei is nothing but 0, 0, 1 on the ith coordinate entry, and then 0. This is ith, the standard basis, that is. Okay, so this is there. Now you see that T, so essentially if you write it like this, so what is the matrix T? Therefore the matrix T, if you want to write it as n cross n matrix, it is nothing but T of E1, okay, T of E2, T of En, right? That is what the matrix T is. If it is given, if the linear transformation is given like this, what is the corresponding matrix? It is of course this, that basically it is determined by how the columns of this matrix. So basically the columns of the matrix is determined by its action on the ith basis vector, okay, by its action on the ith basis vector. Is this fine? Okay, so this is what we are basically trying to do. So basically you see you have a matrix now which is T n cross n such that the first column is T of E1, the second column is T of E2, and then the nth column is T of En. Clear? So see, this matrix nothing but V1, the first column is V1, the second column is V2, and the nth column is Vn, because that's our definition, right? These are the columns. Okay, right. Okay, now you see the thing is these V1, V2, Vn, they are linearly independent. Okay, so since Vi's are linearly independent. Why they are linearly independent? Because lambda i's are distinct, real distinct. Okay, so Vi's are linearly independent. Okay, that will imply that T is invertible. Okay, if you do not, so this is very easy to check. If you do not know that, please check this. Okay, T is invertible, and let's look at what happens to T inverse AT. You see what we need to do? We need to write down T inverse AT as a diagonal matrix, right? Okay, so what happens to T inverse AT? So this is a matrix, right? If we want to determine the matrix, we have to determine what it does on the basis elements, right? So T inverse AT acting at, let's say, EI. Okay, what happens to this? This is nothing but T inverse A. Now T acting at EI. That is the first thing. Okay, what is T acting at EI? This is so okay. So T inverse A. Now T acting at EI is Vj, right? So this is nothing but Vj. So now you see T inverse A acting at Vj. What is A acting at Vj? Now it is A acting at Vj. Okay. Now you see Vi's are, sorry, this is J here. J. Let us do it for J. It doesn't matter I or J, but anyway same. Okay, so you see T of EI is Vi, and Vi is the associated eigenvalue corresponding is the eigenvalue associated with lambda I, right? So this is nothing but T inverse of lambda J Vj, right? Because since this is Vi is the eigenvector associated with lambda I, then A of Vi is nothing but lambda I Vi, right? So this holds for all I. Clear? So this is there. Now T is a linear transformation, that implies T inverse is also going to be a linear transformation. So I can take this lambda J, that's a constant, right? So scalar. So I can take that out, and then I have this lambda J T inverse of Vj. Clear? Okay. Now what is lambda J T inverse of Vj? This is nothing but, you see, T is invertible. So T inverse of Vj is nothing but Ej. Clear? Okay. So what is T inverse of AT? See. So what is the matrix T inverse of AT? Let's look at this matrix. This matrix is nothing but T inverse of AT acting at E1. T inverse of AT acting at EA. Right? That's what it is. So essentially, you see, the first thing is this matrix is nothing but lambda 1 E1. Okay, and then the second one is lambda 2 E2, and the nth thing is lambda n e n, right? Now if you e1 is what, 1 0 0 1, e2 is 0 1 0 0 0. So if you write it down, this is nothing but the diagonal of lambda 1 lambda n. Is this okay? So what did we learn? We learned that if A is a matrix with a real and distinct eigenvalue, this is very important, okay, real and distinct eigenvalues, then of course I mean there are other situations also, but in this situation what happens is you can always find a transformation which actually reduces A. So basically T inverse AT is going to be the diagonal element, okay, right? So let's look at the next situation, okay. So you can take some example. So in the assignment, what we are going to do is we are going to give you some assignments, some problems which actually asks you to find out these transformations for some given specific examples. Now the second case. So this is first case, real and distinct, okay. Theorem 1, let's just call it. Okay. Now before we go on to theorem 2, so basically theorem 2 is about the complex eigenvalues, okay, the complex eigenvalues. Clear? Okay. So now you see that A has a so we will assume that it has a complex eigenvalue, okay. So we know that if alpha plus I, so let A has a complex eigenvalue, okay. So hence if alpha plus I beta is an eigenvalue, of course alpha minus I beta is also going to be an eigenvalue. So the alpha plus minus I beta are the eigenvalues, okay, clear? Okay, so that is always there. Now the thing is this, you see that we have to, we are assuming that of course if alpha plus I beta is an eigenvalue, alpha minus I beta is also an eigenvalue. Okay, now let's say that there can be many different cases, right? So in this case, suppose also we are assuming that A is a 2n cross 2n matrix with distinct non-zero eigenvalues, okay. Also A is a 2n cross 2n, clear, matrix with non-real, so basically complex eigenvalues. What are the eigenvalues? Alpha I plus minus I beta I, okay, I equals to 1 to n. Now you do realize, let's say if you may have this situation that you have a 3 cross 6 matrix, okay, there is this eigenvalues alpha plus minus I beta and then another real eigenvalue. It may happen, right? Okay, so we are not dealing with that case right now, okay. What we are doing right now is we are assuming that you have like a square matrix of 2n cross 2n size, okay, and what happens is all the eigenvalues for now they are non-real, so essentially they are complex eigenvalues, clear? Okay, and we want to see what happens then, okay. So what happens now is this, see that first of all these are complex eigenvalues, okay. So can we we also have associated eigenvectors, okay. So what we will do is we start, let Vj and Vj bar, okay, denotes the associated eigenvectors, or here I wrote I, so let's write down I. Vi and Vi denotes the associated eigenvectors. Okay. Now the thing is this, if let's say summation Ci Vi plus Di Vi bar, let's say is 0, I equals to 1 to n, okay, and Ci Di's are in complex number C, okay, then that will imply that Ci equals to Di equals to 0, right? That is easy to see, okay. So I am not doing this thing. If you I mean, it's better you check this part, okay. So what I am saying is this: Vi is alpha plus I beta, Vi bar is alpha minus I beta. So you just make the real and imaginary part separate, and then you can see that this is true, okay. So Ci and Di, they are going to be 0, okay. So for all I, I'm not writing. So for all I. Okay, now the thing is this: see, we want to we want to find a change of coordinate. So here what we did is, you see, we did a change of coordinate, okay, and after that put it into this form, diagonal form. So we also want to do the similar sort of thing here, okay. So can we do that? Now what do? We change the coordinate of A, okay. So to do that, what we do is this: so now define W 2I minus 1. This we are defining as half of, so the real part of Vi, that is Vi plus Vi bar, okay, and W 2I to be half, sorry, minus I by 2. So that is the imaginary part, that is minus I by 2 Vi minus Vi bar. Clear? Okay. So these are all real vectors. So note W 2I minus I 1 and W 2I are real vectors. Clear? These are real vectors. Okay. So since this is the real part of Vj, Vi, and this is the imaginary part of Vi, so real vectors. Okay. So now we have this this theorem, or let's just put it as a proposition. What is it? It says that the vectors W1, W2, W2n are linearly independent. Okay, is that fine? Okay. So how do you show something like this? Let's look at the proof. So let's say that they are not, right? So then one can find Ci Di, okay, I equals to 1 to n, such that summation Ci W 2I minus 1 plus Di W 2I equals to 1 to n, this is 0. Okay, see, if they are linearly independent, if they are not linearly independent, then this has to be 0 for some Ci Di non-zero. Okay, so essentially what I mean by this is, you can actually find a non-zero Ci or Di, doesn't matter. I mean, at least something has to be non-zero, such that, okay, this relation holds. Okay, now if this relation holds, you see, what is W2I minus 1? That is nothing but half times Vi plus Vi bar, right? And what is W2I? It is the imaginary part. So you see minus I by 2 Vi minus Vi bar. Okay. So if you put it together, what happens is you can write it as I equals to 1 to n. C from here Ci will be there, and the other part is minus I di, and V, you see Vi, clear, Vi plus Ci plus I di Vi bar, right? That's what we are going to get if we are writing it in terms of Vi, 0. Clear? Now you see Vi and Vi bars are linearly independent. Okay, they are linearly independent. What does that imply? So since Vi and Vi bar are linearly independent, clear, then of course Ci equals to plus minus I di. Okay, that is always true. What will that imply? That a real is equals to a complex. That can only happen if Ci and Di are going to be 0. So that will imply that Ci equals to Di equals to 0 for all I. Okay. So that's a contradiction, and hence what happens is W1, W2, W2n are linearly independent. So very, very simple proposition. What basically it says is this: if you have eigen this thing vectors, okay, corresponding to eigenvalues lambda, this thing alpha I plus minus I beta I. So and what happens is those eigenvalues, so basically if you are forming it and you are looking just the real and the imaginary part, they are actually going to be linearly independent. Clear? Okay. Now, so now you see, now, okay, the theorem is done. Clear? The theorem is done. Now you remember we last time in this real and distinct case we just wrote if you are given this thing, a matrix A, T inverse AT, you can write it as a diagonal element, right? Yes, which actually helps us in calculating the exponential. So now we want to do the similar thing here. Now A of W 2I minus 1, what is it? So let's look at this. This is half A of Vi plus A of Vi bar. Clear? See, W2I minus 1 is nothing but half of Vi plus Vi bar. So A of this, A is linear, so I can take it inside, right? So this happens. So now this is equals to half alpha plus I beta Vi plus alpha minus I beta Vi bar. Clear? So that is equals to alpha by 2 Vi plus Vi bar plus I beta by 2 Vi minus Vi bar. Okay. Now if you write it down, this is nothing but alpha times W 2I minus 1 minus beta times W 2I. Clear? So see, now what we are doing is this: we have a linearly independent set of vectors, right? We want to see what happens when A acts on those vectors. So A of W2I minus 1 is this. Clear? Again you have to calculate what happens to A of Wi. Okay, so this you have to check it yourself. Please do this part. Now this is very easy, nothing special is happening here. It is beta times W2j minus, sorry, 2I minus 1 plus alpha times W2I. Okay, so this is what we are, so this you have to check it yourself. Check. Clear? Now you see, we define a map, define T, okay, such that T of EI is nothing but Wi. This holds for I equals to 1 to 2n. Clear? See, W1, W2, Wn are linearly independent. So basically what I am doing is this, corresponding to each, so the unit basis element, I am just mapping it to Wi's. Yeah, just like what we did earlier. Okay, so essentially what is your matrix T? So basically the columns are W1, W2, W2, and that's the thing. Okay, real entries of course. Okay, right. And W1, W2, W2n. So basically you see the matrix T has columns. What are the columns? W1, W2, W2n. Yes, and we just showed that W1, W2, W2n are linearly independent, right? Since they are linearly independent, T matrix is invertible. Okay, so that will imply that T inverse exists. Clear? Okay, now we want to look at what happens to T inverse AT, just like before. See, I want to make it like a diagonal or as close as possible. Okay, I want to make this matrix as a diagonal matrix. Okay, if it's possible. So what happens to T inverse AT? Acting at E, let's say 2i minus 1. Let's look at this. It is nothing but T inverse A, T acting at E 2i minus 1. Okay, and what is E 2i minus 1? This is W 2i minus 1. So T inverse A, it is W 2i minus 1. Now what is A W 2i minus 1? It is nothing but, you see, what is A W 2i minus 1? It is alpha times W 2i minus 1 minus beta W 2i, right? So this is nothing but T inverse of alpha times W 2i minus 1 minus beta times W 2i. Clear? Now T inverse is a linear map, so I can take everything inside. So this becomes alpha times T inverse W 2i is nothing but EI, right? E 2i minus 1 minus beta E 2i. Clear? Now similarly you can check this part, that T inverse AT acting at E2i is nothing but beta times E 2i minus 1 plus alpha times E 2i. Yes. So now let's just write down what is T inverse AT. What is T inverse AT? T inverse AT, this matrix is nothing but T inverse AT acting at E1. Clear? Okay, and it will go on like this, and then T inverse AT acting at E2n, right? So let's write it down if is possible. So you see, it is basic nothing but this matrix D1 Dn. Okay, where Di is a 2 cross 2 matrix, given by you see here alpha minus beta, beta alpha, alpha I, beta I. Okay, and then minus beta I, alpha I. Yeah. If you write it down, you see, I mean, T inverse of, let's say here E1. What is E1? It is alpha. So T inverse AT of E1, it is like alpha E1 minus beta. Okay, E2. Okay, so you put everything together, and this is what you are going to get. Okay, now you again T inverse AT times E2 if you want to calculate, then you just put alpha. So basically you put I equals to 1, I equals to 2, and then you just write it down, then you are going to get a matrix which looks like this. Okay, so the theorem which you are going to get is this theorem. Let A has n cross n has distinct. So A is a n cross n matrix, n cross n matrix has distinct eigenvalues. eigenvalues. Okay, then we can say there exists a linear map such that T inverse AT, how does it look like? T inverse AT, it will look like this. See, lambda 1, lambda k, these are corresponding to the real the real eigenvalues. Okay, so basically you see distinct eigenvalues, it can be real or complex, right? Of course, if they are complex, there is nothing to distinct. So basically the real part lambda 1, lambda 2, lambda k, and for the complex part what you have is this d1, d2, dn, right? So you have d1, d, let's just write it as k, p, okay, p, okay, where d, p will look like this: alpha p, beta p, minus beta p, alpha p. Is this clear? So see, if they are distinct eigenvalues, I am not saying they are real or complex. Let's say there is a bunch of real eigenvalues. So corresponding to real eigenvalues, we know that it will be, the lambda 1, lambda 2, lambda k, right? Now what happens to the complex eigenvalues? For the complex eigenvalues, we know that it will look like d1, d2, dn. So that's what we write, d1, d2, dp. Okay, so that is your T inverse AT. Okay, so if A has distinct eigenvalues, this is what it happens, that you will have a linear map T such that this happens. Clear? Okay, so with this I am going to end this video. In the next video we are going to see what happens when they have repeated eigenvalues. That is a complicated case. Okay.